Okay, welcome back to our continuing discussion of steel morphology. Specifically, we're going to talk a little bit about phase transformations that are taking place on this phase diagram, this iron-carbon phase diagram. And again, I've redrawn this a little bit and added a few things to it. And so let's talk about what we've got on here now. Again, this is the eutectoid reaction region of this diagram. The diagram, of course, is large, very large and encompassing, but we're only concerned about this region basically from about 2% carbon all the way over to about 0, almost 0.025, and then up to this temperature here about maybe 2060 degrees, but that's really meaningless also because we never in our area would ever get something that high temperature wise. But over here is about 1600 degrees, 1650, something like that. But the area where all the transformations are taking place are going to be in this little two-phase region here and this two-phase region over here, because in this area we have 100% austenite structure, which again is our gamma iron, and it's unique because it has an FCC structure to it. And if you want to look at that structure, let me see if you can see this. Okay, this is an FCC structure with these obviously iron atoms located here along. Had the face atoms and the at the vertices. All these atoms, eighth of an atom here at these corners. But notice that because this is an FCC with a maximum atomic packing factor, you're going to have all of these interstitial sites, all these little circles here. All these are interstitial sites where carbon atoms can evade or invade the lattice site here. So there's much greater possibility for carbon, interstitially speaking, to enter into this lattice site on an FCC crystalline structure as opposed to a BCC crystalline structure. So that, again, is our advantage of why we want to try to get this steel up to an austenitic range to try to capture as much carbon into that iron lattice. So because that will give us an advantage when we go to begin to transform this into different metallurgical structures as far as the properties go. So at any rate, this is all FCC, all austenite in this region right here. Now there are two upper transformations line where the phase transformations begin to occur. This one is denoted as the A3 line. This one's denoted as the ACM line. And then we have a lower transformation line, which is this isothermal line here at 1,333 degrees Fahrenheit, called an A1. This is a lower transformation line. These are upper transformation lines. And so things happen on either side of these lines, of course. On the upper transformation line, for instance, on the A3 side here, everything is going, austenite is decomposing now, and it's starting to move into this with the ferrite or the alpha iron here, because this is all alpha iron over here, a very small portion of it. You can see at 0.025, very little bit of that. But when they combine this and this, we start getting this two-phase region where we have a mix of both alpha and gamma iron. Again, this whole diagram is solid. There's no liquid in this diagram anywhere. So, and that is why we call this point right here, which usually might reflect a eutectic point, which would mean it was the lowest melting temperature in the diagram. This is a solid, but it does go, again, from a single phase here to a two-phase here, but both of these are all solid phases. So that's the difference between eutectoid and eutectic. This would be a liquid phase here, and this would be a solid phase down here. if it was eutectic. But this is eutectoid. There is no liquid anywhere. These are all solid phases, of course. Okay, so this lower transformation line is where things begin to change from this two-phase region of the alpha and the gamma down here to now it's going to change from what used to be gamma, which was an FCC, into a complete BCC structure. All right, so everything, this austenite is going to start decomposing. And depending upon where you are, it'll be decomposing either into ferrite plus that mix we call a pearlite, or if it's to the right of this eutectoid composition, the eutectoid composition is at 0.8. If it goes to the right of that, then it'll decompose into cementite and pearlite. All right. Now, again, pearlite, as I mentioned to you before, pearlite is a mix of ferrite and cementite. All right, it's that lamellar mix, those different layers, and we're going to show these on these four microstructures that I've indicated here at A, B, C, and D. A is just above this upper transformation line, completely in austenite. B is just below this upper transformation line. C is just above the lower transformation line, and D is down here completely below the A1 lower transformation line. Okay, so again, we have a couple of quantities here as far as percentages. This is 0.025. This is the maximum amount of carbon absorption into ferrite at 0.025. All right, so that's basically where steel begins to form from just pure iron. And so we go from here to this 0.8, and anything in between here, all right, is going to be referred to as a hypoeutectoid steels, generally speaking. Now, if the carbon content is exactly at 0.8%, that is what we call the eutectoid composition for steel. All of this, just straight line, all the way vertical straight line, from here all the way down, of course, if it's at 0.8%, it's going to be 100% pearlite structure. It's what's they call the eutectoid phase of steel, or eutectoid steel. Anything to the right of this is going all the way up to 2%, which is maximum, is going to be hyper-eutectoid steels. So we have steels that range from less than 0.8% being hypo-eutectoid. At 0.8%, it is eutectoid steels, and then to the right of that, up to 2%, is hyper-eutectoid steels. All right, so those are the categories. Now, let's look at what phase transformations are actually taking place here, and let's start with this first one. But before we do, we need to define a couple of things here, and what we're going to be looking at are microstructures. These are all microstructures. And then we're going to have, with micro constituents. Now, microstructure is just the structural features of an alloy that are subject to observation under a microscope. So this is kind of like what we're going to be seeing under a microscope. And then a microconstituent is an element of that microstructure that has an identifiable and characteristic structure. In other words, it's unique when you see it, you'll recognize it. So that's what a microconstituent is, and that's what pearlite actually is. Pearlite is just a microconstituent, is not a phase. All right. So let's look in here at A up here, and completely in the austenite region, and so we're basically just going to have three, and just putting this up here for ease. This is all going to be gamma grains. All right, solid gamma grains at that point. Now, what we're doing here is we're showing these phase transformations taking place based upon a change in temperature and a change in composition. Now, here we're not really changing the composition. It really doesn't matter what this composition is, but we're not going to change that. But what is changing along this vertical line is the temperature. So that's what we're going to be denoting these phase transformations are, based upon a change in temperature. All right, so if we're just below this upper transformation line right here, what's going to take place here is we're going to have beginning to have some of that change taking place, and the first beginning grains of ferrite begin to form here. And so the lion's share of this will be, and I'm just going to kind of draw these the same way a minute ago, kind of. The lion's share of this will still be the gamma grains, but there's going to be, let's see, I'll just put this color, you can see a little bit better. There's going to be a few beginning formations of alpha grains here. All right, so because we're in this mix, there's alpha. So, and these grains, these beginning grains, always form along the grain boundaries. Okay, so these are going to be the beginning forms of the alpha grains as the temperature drops. Okay. Now, and again, all of these, and this is going to have a special name, by the way. These alpha grains are going to be referred to, because they are formed at above that lower transformation line. We're going to have a special name, and we're going to call them pro or primary alpha grains. Okay, pro or primary alpha grains. So they are going to begin to form, and they will continue to form. So as the temperature drops, we're going to, and by the way, when we get down here to see, as the temperature drops, we're still going to be alpha grains. Okay, so let's draw that in here.